Welcome to What Did the Code Say? I'm your host, Dragon Megalodon, and today we're tearing into the source code of the universe's absolute favorite mathematical curve, the parabola.
But first, subscribe to the channel and hit the bell right now. Let's get right into it. How do we debug heavily obfuscated standard math formulas to find the vertex? Look, if you're programming physics in a game engine or optimizing a cost function, you're absolutely going to encounter quadratics. The challenge is that standard equations don't just hand over that sweet vertex data, like exactly how high that jump goes or where that minimum cost bottoms out.
Here is our debug sequence for today. We're going to hit the anatomy of a quadratic, graph the parabola, compare standard versus vertex form, hack the vertex formula, and wrap up by running through some slick form conversion tricks. Let's go.
All right, section 1, anatomy of a quadratic, basic code syntax. So, any quadratic function is basically a script running on this foundational logic. f of x equals ax squared plus bx plus c. Translating that math jargon into reality? Those letters a, b, and c are just real numbers. They're your fundamental parameters. You tweak them and how the curve behaves changes. For example, c is usually your starting height in a physics sim, literally where your character is standing before they jump. But there is one strict unbreakable rule in this logic gate. Your a variable cannot equal 0. That x squared term right at the front, that is the absolute hallmark of a quadratic function. It's the engine that gives the code its signature curved geometry. And stepping back to look at the math brilliantly illustrates a huge, common beginner syntax error. Think about what happens if you actually allow a to equal 0. 0 times x squared is, well, 0. The x squared term gets completely wiped out of existence. Your code just degrades into f of x equals bx plus c. Congratulations, you just broke the parabola. By killing that squared term, you flatten the entire function into a completely straight line, a simple linear equation. You always need to preserve that x squared term for the curved logic to actually work.
Moving on to section 2, graphing the parabola, turning code into visual shape.
When this raw mathematical code executes visually on a coordinate plane, it forms a perfectly symmetrical U-shape called a parabola. Now check out that leading coefficient again, the a parameter. It acts as a primary directional flag. If a is greater than 0, so a positive number, the parabola opens upwards, making the vertex the absolute lowest point, the valley. Think of it like a giant satellite dish pointing at the sky. But if we hack that variable and make a negative number, the entire geometry reflects vertically. It's literally like flipping the gravity in a game engine. The parabola opens down, and boom, the vertex instantly becomes the absolute highest peak.
So how do we find exactly where this curve crashes right through the x-axis? In a lot of programming scenarios, the x-axis represents the literal floor. The x-intercept is the exact frame your character hits the ground. The algorithm for this is super straightforward. Step 1, set y equal to 0, because 0 is the mathematical elevation of ground level. Step 2, solve for x using the classic quadratic formula. That computes the exact coordinates where your curve intersects the horizontal baseline. Just like that, you've located your collision points.
Section 3, standard versus vertex form, comparing the formats. Let's look at the two primary ways developers write this code. First up, we have the raw compiled look of standard form. Y equals ax squared plus bx plus c. It's incredibly clean for a computer to process, but man, it actively hides its geometric secrets from human eyes. In contrast, we have vertex form. Y equals a times the quantity x minus h squared plus k. Visually comparing these two reveals a massive structural advantage for vertex form if you're the one who actually has to graph it or interpret the physical data. Which brings us to a crucial realization, captured perfectly right here. When a function's in vertex form, it's easy to read off the vertex. It's just the ordered pair h, k. This is the ultimate developer's shortcut, guys. If you're calculating the max height of a projectile or the absolute lowest cost in a financial model, that answer is the vertex. And in vertex form, that peak or valley is literally hard-coded right into the parameters as h and k. You don't have to run a single complex calculation, you just look at the code and read the variables out loud.
Section 4, hacking the vertex formula. Time to hack standard form.
But what happens when you aren't so lucky? If your function is locked in standard form, you can't just casually read the vertex. The data is totally obfuscated. That's when we deploy this cheat code, the vertex formula. The x-coordinate of the vertex in standard form is always exactly negative b over 2a. It's incredibly efficient. Say your b is 4 and your a is 2.
You just divide -4 by 4, and your center x-coordinate is -1. Instant. You pull those coefficients straight out of standard form, run that quick division, and you completely bypass all the messy algebra to find the exact center of your parabola.
Now, as coders who actually care about our craft, we never just copy-paste a formula without understanding the framework. It's dangerous to rely on magic. So let's figure this out together. Why does the -b/2a hack actually work under the hood, perfectly, every single time?
Let's reverse engineer the logic by looking at the full quadratic formula used to find those x-intercepts. It starts with -b/2a, and then you've got that massive complicated square root part being added or subtracted. Well, that square root is just a physical distance. Because parabolas are perfectly symmetrical pieces of geometry, the vertex has to sit dead center between your two intercepts. Think of it like walking. You start at -b/2a, and you add the square root distance to walk right, or you subtract the square root distance to walk left. So what's sitting perfectly in the middle of those 2 points? Just your starting position, -b/2a. That mathematical midpoint is your vertex coordinate. It's a beautifully elegant piece of logic hiding right in plain sight.
All right, Section 5, Form Conversion Tricks, Compiling Formats. Sometimes your project requires you to switch formats entirely. Going from vertex to standard form is basically just unpacking a zip file. Step 1, expand that x minus h squared binomial. You actually write it out twice and multiply it using the FOIL method to get your x squared terms. Step 2, take your leading a coefficient and distribute it mathematically across all those brand new terms you just created. Step 3, clean up the code. Just combine whatever constant numbers are lingering on the tail end. Execute that standard arithmetic and you have successfully reformatted the curve into clean standard form.
Going from standard to vertex form, however, requires a bit more careful reverse engineering to rebuild the coordinates piece by piece. Step 1, use our master hack, x equals -b/2a. That finds the exact x-coordinate of the vertex, which becomes your h parameter. Step 2, remember that a mathematical function is just a machine. Every input x needs an output y. So take that x you just found, plug it completely back into your original standard equation, and compute the result. That result is your y, which serves as your k parameter. Step 3, your leading a value stays entirely identical to the original equation. Drop all 3 of those values, a, h, and k, straight into the standard vertex template, and your conversion is totally complete.
So if you ever get lost in the code, here is your cheat sheet summary. Take a second with this. If your goal is to find an x-intercept, meaning where it hits the ground, your method is to set y to 0 and solve. If you need to find the vertex, but you're stuck in standard form, you run the -b/2a hack. And if you need the vertex and you're luckily in vertex form, you just read the h and k parameters directly off the screen. It's the ultimate reference table for any beginner coder dealing with the geometry of quadratics.
In summary, the specific mathematical form of your quadratic code dictates your decoding strategy, and the -b/2a formula is your absolute skeleton key for unlocking standard form. If you want to understand what the code says before it explodes, hit subscribe right now. Don't forget to like. This tells YouTube that technical content is still alive and highly relevant. And please, share this explainer with a beginner coder who desperately needs a mathematical lifeline for their project today.
We've hacked the quadratic, found the vertex, and perfectly mapped out the entire parabola. And you? What did the code say in your project today?